Hello. So today we are going to start chapter 11 about covariance and the correlation coefficient. So actually this is the second last chapter of this course. And let me briefly describe where this chapter fits in our course. So the ultimate goal of our course is to introduce the regression model. The regression model is the workhorse model for most of the empirical analysis in economics, right? So if you take like say money and banking, finance, like labor economics, industrial economics, like international trade, whatever you learn, the data analysis, like more than 90% of the data analysis is based on some kind of regression model, which we are going to learn in chapter 12, the last chapter. So to get there, we learned we went through many chapters like probability, like a mean, median, variance, standard deviation. And then we learned like binomial distribution, normal distribution, sampling distribution, estimation, hypothesis testing. We learned a lot of techniques, a lot of measures, and now we are just one step away from the last chapter, right? So think about this. What we learned earlier is like mean, median, like variance, standard deviation. Those measures are for a single random variable, normal distribution, binomial distribution. They are also for a single variable. Most of what we have done up to here are based on single variable analysis, right? But in many analyses in economics, we are interested in the relationship between two variables, how one variable affects the other variable, how they are related, if they are positive related or negative related, things like that. So we need to learn how to handle multiple variables, and that's what the regression model does, right? So that's what we are going to learn in the last chapter. But before learning the regression model, we first need to understand some basic measures to handle multiple variables. They are the covariance and the correlation coefficient, like in this chapter. So we are going to prepare ourselves before we learn the regression model, which is the most important chapter of this semester, right, in this course. Okay, let me start with real data. Right, it's not a fake data; it's real data. So we have data on 183 countries about their temperature and their GDP per capita, right? So it's a kind of interesting data. So the temperature is average annual temperature in 30 years and measured in Celsius. And the GDP per capita is measured in US dollars in 2005. So here is the data, right? We have like country names and temperature and GDP per capita, right? So we have many countries, many observations up to 183, excluding the first row, which is the slot belt, right? So then let's just have a look. Like, by the way, in case you didn't know these functions, the sort and filter, if you click filter here, then you can like check like this, right? For example, you can order, rearrange, sort the observations from the largest to smallest. So let's do this. The richest country in our data is Qatar and Luxembourg, Macau, Singapore, Kuwait, Norway, Brunei. So we can list the data using the filter function, or you can sort from the smallest. The poorest country is Congo, Liberia, Eritrea, Burundi, Niger, like that. Also, you can check coldest country, Canada, Russia, Mongolia, Norway, as expected. All right. So it's interesting to play with this. Anyhow, we have data about like data on 183 countries, on their temperature, on their GDP per capita. We are interested in how they are related, right? Like for example, colder countries richer or poorer. Like it's interesting. Like if a country is warmer, then is it more likely to be richer or poorer? So just their relationship is of our interest right now. Then the first thing I recommend you to do is to draw a scatter plot. So the x variable is the temperature and y variable is the GDP per capita. And then you can draw a scatter plot like this. There are 183 points, dots on this plot, and each dot represents a country, right? So the horizontal variable is temperature. So the coldest countries are here, and hottest countries are here, like Canada, Russia are here, and Norway, Luxembourg, and Macau, Qatar. Those countries are the richest country. The higher, the richer, the right or hotter, the left colder, right? So you see the distribution. You can do that on Excel, like choose the data and click insert, and you will be able to find this chart, scatter plot. And if you just click it and just click it, then you will see chart. Oh, excuse me. Yes, right. This is temperatures, and this is GDP per capita. So, oh, no. I'm sorry. So you have to choose only these two variables, and click scatter plot. Then you get the scatter plot of GDP per capita against temperature, right? So it's click like it's just simple clicks to generate a scatter plot in here. Okay. So what do we like to do here? So you just see the pattern where the countries are located on this two-dimensional plane by drawing a scatter plot. And more specifically, our question can be described this way. First, we are interested in the direction. Do cold countries have higher GDP or not? Right? The colder, the higher GDP per capita or not? That is a direction. And second, how strong is the relationship? Are these two variables related to each other strongly or not much, right? So these are our two main questions in terms of the relationship of these two variables. And then to answer those questions, what we want is to draw a trend line. So by drawing a trend line, we can answer both questions. First, if the trend line, we draw a trend line like this. The red line is the trend that going through the center of the dots. And if this trend line is going down, that means as a country gets hotter, the GDP per capita is getting lower, right? As it goes to the right, the slope goes down. The trend goes down. So we can tell that the direction is negative, right? Colder countries are richer, and warmer countries are poorer. That's what you can tell from this red trend line. That's one thing. And second thing, how do we tell the strength? Strength is about the deviation from the trend line, right? So for example, Qatar is an extreme deviation because the trend tells that hotter countries are poorer, right? Usually warmer countries are poorer, but Qatar is the richest country in our data, but it's one of the warmest country too. So it deviates a lot, right? There are some countries that deviates a lot. So in that sense, it's not that strong. The relationship is not that strong. That is a simple conclusion by just looking at the scatter plot. However, we would like to quantify that. It's just what I just said is eyeballing, like describing how it looks like, but it is not scientific enough, not quantitative enough. So we are planning to quantify those measures, the direction and the strength of the relationship using the trend line. Okay, that is the goal of these measures, the covariance and the correlation coefficient. Right? By the way, before proceeding, I have a word of caution. Um, what we focus on is purely a linear relationship. What I'm saying by linear relationship is the trend is, we assume that the trend is linear. So the trend must be a straight line like this, right? Even though it's I'm not sure if it's linear, but I assume that trend line must be straight. That's kind of limitation of our analysis, but we need it for simplicity, right? For example, if the trend is clearly not linear, then our analysis does not work well. For example, if you see data like this, then it's not linear. The trend is going down at first and then go up again. So the trend is, U-shape. It's not a straight line. Also, in this example, the trend is not linear because it's flat up to here and then slope changes. There is a kink. There is a kink in the trend. So, like technology development was slow in the past, but at some point it explodes. Something like that. So these are examples where our measures does not work well. But many of our examples, many of economic data, most of economic data are like a show linear relationship, and linear relationship is sufficient in most applications. So that's why we limit our attention to linear relationship, right? More complicated cases, there are more complicated examples, and you are going to learn that in the next data analysis class, like 420, Eco 420 will introduce a few nonlinear relationship cases. But in this chapter, we will limit our attention to linear relationship. Okay. And then, think about linear trend and the direction. Depending on the direction of the relationship, you can think about like a negative relationship like this. Negative relationship will have a declining straight line as a trend line. The trend line, straight trend line will go down. And if there is zero relationship, it should be flat. The straight line should be flat. And in positive direction relationship, you will see increasing trend line. So imagine when I say the direction of the relationship, it's about the slope of the straight trend line goes down or go up, right? That's what I mean by the direction, okay? And the strength, by strength, I mean even though the direction is given, the trend line is the same, you can imagine different scatter plots depending on how scattered those observations are away from the trend line, how tight the distribution is, or how scattered, how spread out the observations are. It's about deviations, okay? So that they are the direction and the strength of our relationship. So then, how do we quantify that? Our idea is, first, we will measure the direction of the relationship. The idea is, when I say positive direction, that means when x variable increases, y tend to increase. Or vice versa. Like when x variable decreases, y variable decreases. In other words, they move together. When one increases, the other increases. And when one decreases, the other decreases too. Like as a tendency. So that means a positive relationship. If they are a negative relationship, then of course like if one increases, the other will decrease, right? So we have to quantify that, and the idea is we are going to divide our observations into 4 quadrants, right? So the basis is the origin of the quadrant is the mean. We choose the mean of the average of x and average of y as the center and divide the observations into 4 quadrants, right? So the first quadrant in the observations in the first quadrant will be interpreted as x increased from its mean, its average, so it's right side of x bar. At the same time, y also increased from its mean. Y is upper, like upside, top part, like upper area of y bar. So y also increased from y bar, x also increased from x bar. So the first quadrant imply both x and y increase together. They move together. Similarly, the third quadrant here shows the observations that x is decreased from x bar and y also decreased from y bar. If everything started from the mean, both decreased. So they also move together. They are the observations that are moving to the negative direction together. But the second and the fourth quadrants are the opposite directions. They are the observations with negative relationship when one variable increased but the other variable decreased, right? X increased but y decreased, or x decreased but y increased. So the second and the fourth quadrants have show the negative relationship. So then, okay, the idea is okay to define what are positive relationship and what are negative relationship. But still, how do we quantify that? The idea is by multiplying the deviations, right? How much x observation increased or decreased from its mean versus multiplied by y deviation, like deviation in y minus y bar. How much y increased or decreased from y bar, right? If they move to the same direction, like both positive or both negative, then when you multiply them, the sign will be positive, right? So that's exactly what we want as a positive relationship. So when I say an observation shows positive relationship, that is the deviation in x and y are in the same direction, so their multiplication will be positive. And also, they are the observations on the first and the third quadrants, right? So these two quadrants include the observations with positive relationship. And the negative relationship will be will have negative product. Like when you multiply the deviations in x and y, so when x deviation is positive, then y deviation will be negative if they had a negative relationship. So their multiplication will be negative, right? So the second and the fourth quadrants have observations that have negative relationship. So their deviations will yield negative products. So this is how we quantify whether a observation is positive or negative relationship. Okay, but this is just like the cross product of deviations are for each observation. So if you have 100 observations, you can define these cross products for each observation. So you are going to have 100 products. So we are going to take the average to see if which sign dominates. So this much in this graph, in this scatter plot, the first and the third quadrants observations are positive relationship, and the second and the fourth quadrants are negative relationships. So then, but we have to determine what is the overall relationship, what is the dominating sign to do that, we take the average of the cross products of deviations, right? So like this. So we have x deviation and we have y deviation, and we take average, right? Sum and divide by the sample size. But remember, like when we learned the variance in chapter 4, we learned that there are two formulas, sample variance and population variance. And the reason why I recommended the sample variance is because sample variance is unbiased, but the population variance formula is biased. We learned that in chapter 8, chapter 9 or 8, I'm not certain. So anyhow, here we have the same problem. So we are going to calculate the covariance, which is a kind of average, weighted sum, like so average, but we have to use n-1 in the denominator for this covariance estimator to be unbiased. So the sample covariance formula uses n-1, which is more common, which is unbiased. But there is another formula called the population variance formula that uses n as the denominator. This is okay. You can justify that, but it has a bias, right? So it's pretty similar to the variance. Actually, variance is a special case of covariance because if you replace y with x, so x deviation and here y deviation, but if y equals x, then it is x deviation squared in the end. So x deviation becomes x deviation squared. So the covariance of x comma x equals the variance of x, right? So in that sense, you can generalize the variance as a special case of covariance with the random variable itself. Okay, anyhow, I defined the covariance to quantify the direction of the relationship. The idea is we divide data into two groups, positive relationship group and negative relationship group, and then we take the average to see which sign dominates, right? That is the key idea, and you get the sample covariance formula, and it nests the variance as a special case. Okay, so in the next video, I will bring a numerical example to practice how to calculate the covariance. Okay, thank you for watching. See you later.